It's Mike again. As you all know, you can protect your unRAID array using something called a parity drive. Most people don't understand how this technology works and are usually quite surprised to find out it's actually very simple math that makes the parity drive work. The other question that people usually ask is, why does my parity drive have to be the same size as the biggest drive in my array? And I'm going to explain that. And the other part that I hear a lot is, how can one parity drive protect an entire array of other disks? And I'm going to tell you how that works. It's actually quite simple. I'm going to try to break this down into just a few-minute video, and I'm not going to go into what's involved with multiple parity drives. So this is going to be an example of a single parity drive protecting an array, which is what most people are going to be, or how most people are going to use their unRAID server. If you're interested in knowing how multiple parity drives work, it's not that much different, and I'll be happy to go into that. But for now, I'm going to focus on trying to keep this simple so you understand how the parity drive works, you understand why your parity drive needs to be the biggest drive in the array, and how, when you lose a single drive in your array, how you can recalculate the data that was on that drive and replace it and avoid data loss. So I put together some slides. You're not going to see my beautiful face through these. I'm just going to try to explain it as we go through. Feel free to put questions below. If you like this video, please click like, and I'm super honored and humbled if you click subscribe. Thanks. Let's get started. So let's start with what is the most basic question here. That is, what is parity? It's a system used by most data storage systems, whether it's a traditional RAID array or what we have on unRAID here, to ensure data integrity. In simple terms, basically what that means is it's ensuring that the data that's existing on the disk is correct. So when you read a file off the disk, you're ensuring you're getting the correct file and not a corrupted file. And secondly, to provide the ability to correct that data when it is not correct. So if you have let's say you got one disk and the file comes off, you can detect that that file has been corrupted and calculate what that file is supposed to look like so you get the actual data that you've requested. Now, the way unRAID works is it uses a system called even parity. In short, as we all know, all data stored on any kind of storage device, whether it's a hard drive or USB stick or even in memory, is always stored as a 1 or a 0, which is binary. There's the only two states that data can be in on magnetic media. unRAID uses something called even parity. What that means is when you add up all the bits you're supposed to get back, they must result in an even number. Now that's going to confuse you right now, but I'm going to try to make it make sense in the next couple minutes. So let's look at an example here. Let's say we have a system that's got 4 data drives in it and 1 parity disk, so a total of 5 drives. In this case, let's say 4 of those drives have data stored on them, and in each disk, it's got and this is just one sector, so on each disk, you've got a value of 1. So if we add up those 4 bits on those 4 drives, we have 1 plus 1 plus 1 plus 1. I think any of us can figure out that that's 4. 4 is an even number. Now, because this is even parity, whatever our calculation is needs to be an even number. So in order to keep this an even number, we have to set our parity bit to 0. And as you can see here, our parity bit 0. So once again, we have one sector across 4 drives. Each one has set to a bit of 1. In order to keep that as an even number, we set the parity disk to 0. Pretty simple, right? Let's look at one more example. So let's say we move to the next sector on the disk. I'll call this example 2. In this case, our 4 data drives have the stored values of 1, 0, 1, and 1. Using our advanced college level math, we can calculate that that equals the value of 3. So 3 is an odd number. Therefore, we have to set the parity bit to 1 to create an even number of 4. So again, we add up 1, 0, 1, 1. That comes to 3. And then we set our parity bit to 1 so that we have an even number of 4. This will start to make sense when we start to look at how we reconstruct data when it's corrupted or otherwise missing. So let's ask ourselves again, when is parity used? Once again, it's used in exactly two situations. When a bad disk is being rebuilt, so your drive's blown up and or it's failed or otherwise gone where dead hard drives go, which is never a good place. And you need to replace it, and then you're going to use your parity information to rebuild the data that was on that drive, so at the end of the day, it looks like nothing ever happened. And the second time is when a bad sector is detected. In both these cases, we're going to be missing information, and we need to look at the existing information we have and use that parity calculation to identify what was supposed to be in that sector we're trying to read. So essentially, we're going to use math to take the existing information and learn, or at least calculate, what it is that's missing, so that when we receive our data from the server, it is what we expect. So let's see how that works. So looking at example 3, this is going to be our disaster example. Our third drive is now gone. We have a new disk, we can replace it, but it's blank. All the data is not on there. So how is unRAID going to know what was on that disk? We're putting that disk back in, we're asking unRAID, hey, can you tell me what was on that disk? Now there's two things that happen here. One, while that disk is missing, unRAID is still going to give you the information that was on there, which is actually really cool, and this is the part that looks like magic, is the disk is missing and you don't know it because it's recalculating in the background and giving you the information that was there. Keep in mind, while that disk is missing, you're unprotected if another drive fails. That was another video. But right now, we want to replace this drive, and we're going to ask unRAID, go ahead and fill up this drive with the information that was there on the disk that's now missing. So let's see how that works. So to recap, our third hard drive's gone. We have a new disk, it's blank. How's unRAID going to know what was on that disk? The information we have right now is we have a parity disk, which on this particular sector is got a value of 0. We've got the first hard drive, which has got a value of 1 in this sector. Second hard drive, which has got a value of 0. And our fourth hard drive, which has got a value of 1. What we don't know is what's supposed to be on that third hard drive. So, believe it or not, we have enough information here to determine what goes on that sector in that hard drive. And again, this is sector by sector. So we're going to go through each sector of the hard drive, and for each sector, figure out what's on that missing drive. The short version of it is we're going to solve for x. You all remember that from your high school math courses, except this is going to be a lot simpler, and hopefully you all pass this test. So let's look at sector 1. We have a parity bit of 1, first hard drive value of 1, second hard drive value of 0, and the fourth hard drive value of 1. So let's take a look. So we got 1 plus 1 plus 0 plus x plus 1. We need to know what is x. Now we already have the answer because we know it has to be an even number. And if we add the values that we know about, 1 plus 1 plus 0 plus 1, that comes out to a value of 3. That's an odd number, guys. That means x has to be 1. There's no other way that that could work. So we put a 1 in that sector. We now know what was missing on that hard drive. Let's go to the next sector. In our next sector, we have a parity bit of 1. We have the first hard drive with the value of 0. Second hard drive with the value of 0. We don't know what's on the third hard drive yet, but the fourth hard drive is a value of 1. So if we add up those two parity bits, we get 1 plus 0 plus 0 plus 1, which comes to a value of 2. This is an even number. Therefore, we know automatically that that missing hard drive has to have a value of 0. If it didn't have a value of 0, if it had a value of 1, it would be an odd number. Therefore, the value must be 0. And we've now rebuilt that sector. It's pretty easy at this point, doesn't it? And we repeat that process for each sector, and each sector, and each subsequent sector over and over until we've actually rebuilt that entire missing drive. It's almost like magic, but it's actually just very simple binary math. But to non-tech folks, it looks like magic. And if you don't understand this basic math, it looks like magic also. Like I said, a lot of folks do not understand how one parity drive can protect an entire array of 10, 11, 12 drives within the unRAID system, whereas normally you lose about 20% of your, you lose about whatever one drive is in your array of RAID 5, whereas this just seems much more efficient. because we have a separate parity drive as opposed to building the parity into each of the other drives on a stripe system. So again, not magic, just very basic math. Let's look at the age-old and often asked question: why does the parity disk need to be as large as the largest disk? It's actually quite simple. Let's take a look at a typical array of mixed size drives. So in this case here, we have a parity disk of 8 terabytes. Our first data drive is 8 terabytes. Then we have 3 other data drives ranging in size from 4 terabytes to 3 terabytes. Obviously, this parity drive will protect the entire array, but why couldn't we have like a 4 terabyte parity disk as opposed to having to waste an entire 8 terabytes on it? Once we have an 8 terabyte data disk, the next biggest data drive that can be out there is 8 terabytes. If we want to put a 10 terabyte drive in there, we're going to need to have a 10 terabyte parity disk. Let's see why that is. The main reason is that the parity drive needs to have a parity bit for every single possible sector in the array. As you saw when we were doing reconstruction, we were going through sector by sector and making that calculation based on each of the other drives and the values that are there, trying to determine what is the only possible value to put on that particular drive. What that implies is that that parity disk has to have at least the same number of sectors as the largest disk. Let's look at an example. So in this example, I'm going to take a sector that's located at exactly the 7 terabyte mark on our second drive, which is our 8 terabyte drive. And let's just say that that sector has a value of 1. Now, clearly on our other 3 data drives, we've got 4 terabyte, 3 terabyte, 3 terabyte, there is no 7 terabyte mark. So how does unRAID deal with the fact that those drives are smaller and there is no 7 terabyte mark on those drives? Essentially, any sector that exceeds the size that we're reading, we're going to just return a 0. Okay? So on my 4 terabyte drive, if I'm looking at a sector on the 7 terabyte side, at the 7 terabyte mark, clearly that doesn't exist, so unRAID is going to return a 0. Same with the other 2 3 terabyte drives. So no matter what happens, those 3 drives, anything beyond 4 terabytes or 3 terabytes in the case of the smaller ones, are always going to return a value of 0. So if we're calculating parity for our 7 terabyte mark, of which we only have one drive that actually has that particular amount of storage, and that's got a value of 1, we're going to do our calculation. If we look at our 4 data drives here, we're going to have a 1, which is an actual data, plus our simulated data of 0 and 0 of 0, because those drives don't actually have that sector. So we're going to return 1 plus 0 plus 0 plus 0, which is odd, right? It's an odd number. What's our rule? Our rule is the parity bit the rule is our parity check always has to equal an even number. So to make this an even number, our parity disk is going to record a 1 at that sector. If that sector were empty and it had a 0, in order to make it even, the parity drive would record 0. It would be zeros across the board. Make sense? So let's look at this logically. Let's say you wanted to use a 4 terabyte parity disk, but we still have an 8 terabyte data disk. If you were going to do that, and you looked at your value, 1 plus 0 plus 0 plus 0, like we just talked about, in order to make this work, you would need a parity bit of 1. But if you're on a 4 terabyte drive, there's no place to put that bit. You're already past the limit of that drive. So if unRAID even allowed you to do this, which it doesn't, by the way, but even if it allowed you to do this, anything beyond your 4 terabyte mark would be completely unprotected, and that's really unacceptable and defeats the whole point of parity. That's why your parity disk has to be at least as big as the biggest drive in your array, because he's got to be able to map a sector to every sector on that disk in order to do the parity calculation. So in short, just to summarize, parity is simply a single bit for each sector on an extra drive to ensure that the bits in your array all add up to an even number. It's really that simple. This is why when we also clear new drives to 0, when we add them to the array, or this is why we do that. Because when let's say you have 4 drives and you want to add a 5th drive, if that drive is completely cleared to 0 and you put it out there, it doesn't affect your parity calculation at all. Because if it was an even number before and you add 0, it'll still be an even number. Now as you start writing data to that new drive and flipping some of those bits to 1,
The write process will recalculate your parity and update the parity drive accordingly. In addition, there's also a schedule that runs monthly. You can make it more frequent if you want, that actually recalculates your entire array of parity. That's a parity check. Highly recommended you do. It roots out any corruption that could be happening. Anyway, third point, the parity drive must be the largest disk in the array because it has to have enough storage for each bit on the largest drive in the array, whereas smaller data drives can assume 0 bits for all space beyond their storage capacity. The smaller data drives can assume 0 when you're trying to map up to a larger drive, but your parity drive can't because it needs to do calculations and it needs to store those calculations for the largest drive. Simple math makes it possible to reconstruct failed drives or ensure data integrity, and that's really the entire thing. I'm hoping I've made this parity very simple for you. I've wanted to do this video for a very long time. I don't think there was actually a really good video out there explaining this, so I'm really hoping I've been able to communicate how this works, and hopefully you better understand your unRAID system and make better use out of it. If you have any questions or you need clarification or anything, feel free to put them in the comments below. If you like this video, click the like button. If you don't, the other button works too. And if you're interested in this topic or other systems integration topics and storage, please subscribe. I'd really enjoy that. Thanks. Take care. This is Mike.